discussion. Okay. So yesterday we are discussing about Routh stability criterion. Why we need to go for Routh array, that we have seen with two examples, right? So according to Hurwitz polynomial, coefficients, all the coefficients of a polynomial should be non-zero, and the sign, what about the sign? And the sign also should be same. In such case, all the poles will lay on the left hand LHP of the S plane, right? But this is true, means this for first order system and the second order polynomial, these are the necessary as well as sufficient condition to check the stability of the system, right? But we have seen two examples for a third order system, that is D1 of S and D2 of S, and it is observed that that condition, Hurwitz condition, means all the coefficients must be zero and all the coefficient signs should be same. That is only a necessary condition, right? Because here in these two examples, for D1 and D2, all the coefficients are not zero and the sign also same. But it is observed that for the second case, two poles are lying on the RHP. So the conclusion is that condition is not a sufficient condition. That is only a necessary condition to check the stability of the system using the system characteristic polynomial. So what is the sufficient condition? That is, we need to construct a Routh array, and today we will see how to construct that Routh array, and from Routh array how can we find out the location of the poles. Okay, so our aim is to locate our poles, whether it is located in LHP or RHP or it is in the imaginary axis. Clear? Yeah. So this is very simple conceptually. We know our polynomial is a naught s power n plus a1 s power n minus 1, something like that, right? So the first step is you have to write the power of s from higher order, from the higher order to the lower. So for an nth order polynomial, the first s is s raised to n. The next one is s raised to n minus 1, s raised to n minus 2, etc. up to s power 1, s raised to 0. So first step, you write all the s times from the higher order to the lower order. Okay. Now let us see how to construct this using the polynomial. So that you take the first two s, say this s power 1, sorry, s power n and s power n minus 1. And now you locate the coefficients likewise. See, our first coefficient is a naught, right? So a naught you have to place here. The next one is a1, that you put it in the next s power 10. a2 you have to locate here, a3, a4, a5, a6, a7, right? It will go like this. So this is the second step. First you write your s power of s from higher to lower, then you take the first two s's and locate the coefficients accordingly, right? Now say here the value is b1, b2, b3, and here one more time I will write s power n minus 3. Okay. This is z1, z2, z3, likewise. So how to find this b1, b2, b3? So we need to find b1, b2, b3, right? So b2 is nothing but, sorry, b1 is equal to, you just multiply this. what will get? A1, A2 minus multiply this. That is A0 into A3, the whole divided by this first element, A1. Clear? Now, accordingly, how to calculate V2 this time, this magnitude? You have to do like this. You have to multiply A1 with A4. You will get A1 A4 minus A0 A5. A0 A5, the whole divided by this time. A1. Clear? Likewise, you can find. So, how will you calculate Z1? How will you calculate Z1? You multiply these two times, that is B1 A3 minus A1 B3, the whole divided by what will come? B1. Clear? Now, similarly, you can find Z2 also. C2 can be found out by like this, B1 A5 minus A1 B3, the whole divided by B1. So likewise, you can find all the values in the Routh array. And what Routh is telling is, after filling all the values, take the first column. So this is the first column, right? So according to Routh array, what he is telling is, if there is any sign changes in these values, then the number of sign changes in the first column is equal to the number of roots in the RSP. Clear? So first, after constructing the Routh array, what you have to do is, you take the first column and check is there any sign changes occurred in the first column. Actually, for a stable system, the number of sign changes should be 0. There should not be any sign change. Sign change in the sense plus to minus, minus to plus, something like that. So if there is no sign change, it means that all the poles are located in the LHP. Okay, so we will write that condition. So the sufficient condition, necessary condition, we already seen. What is the sufficient condition? You construct Routh array, and the sufficient condition is the number of sign changes in the first column of the Routh array. First column of Routh array should be 0. Should be 0. Right? So the one important observation is the number of sign changes. Suppose there is number of sign changes, that means the number of sign changes in the first column of the Routh array is equal to the number of roots in the RSP. Suppose I have 2 sign changes in the first column, it means that 2 roots are located at the RSP of the plane. That is the conclusion. So by using this Routh array, you can check the stability of the system. This you keep in mind. Now we will see some numeric examples. So by the time we will be, so this is the sufficient condition. Okay, now we will take the same polynomial. We already seen two polynomials, right? D1 of s and D2 of s. The same polynomial we will take and check the stability, whether it is coming correct or not. We will validate our roots array concept. Okay. So first you take this example. So what was that polynomial? D1 of s is equal to s cube plus 2s square plus 3s plus 1. So by using the Hurwitz concept, we are not able to differentiate it, right? The two polynomial. Now we will check the stability using roots array. So how we can write? What is the highest order polynomial? Highest order. What is the highest order? 3. So we can write all. We can start from s power 3, then s square, s power 1, s power 0. Right. So what is the next step? Locate the coefficients. Right. So our a1 is what? 1. This is 1, right? So you locate all the coefficients of s. 1, 2 you have to place here. 3, 1. Yeah. Now you have to find the value, this one, right? How will you find? Multiply this and this. How much it will come? 6 minus, again you have to multiply this. So 6 minus 1 is 5 divided by 2. The constant value is 5 by 2. Right? Since there is no coefficients after this, this can be set as 0. Right? Here there is no element hereafter, right? So this will be 0. So how will you find out this? Just multiply this with this and minus this, right? So 5 by 2 into 1 minus 2 into 0, that is 5 by 2 divided by 5 by 2, it will become 1. So now we have formed the root array. We have formed the root array. Right? So this is the first column. First column of the root array. So what is the observation from this? Is there any sign changes occurred in the first column? No, right? Yeah, because this is plus, this is plus, this is plus, this is plus, this is plus. All the values are positive only. That is, number of sign changes is equal to 0. So what is the meaning of that? How many roots are there for this polynomial? 3 roots, right? So the conclusion is, since the number of sign changes is 0, all the 3 roots lies on the RSP or LSP? LSP of the, yeah, LSP of the S plane. So since all the roots lies on the LSP of the S plane, we can say that it is a stable system, right? Yeah. Now we will consider the second polynomial, that is D2 of S. What is the polynomial? Just to swap this values, right? So it is s cube plus 2s square plus s plus 3, right? Now this polynomial also, all the coefficients are non-zero and all the signs are the same, right? Now we will apply the root array concept and see whether the system is stable or not. So like this, we can place all the order of the s cube, s square, s power 1 and s0. So coefficients can be 1, 2, 1, 3. So what will be this value? Just multiply this and this. That is 2 minus 3. It is minus 1 by 2. Right? Since there is no coefficients in this side, we can put in this as 0. and this will become 3, right? So this is our first column. So you can observe that there is some sign changes, right? How many sign changes are there? 1 or 2? See here this is plus, this is plus, this is minus, right? So one change is from plus to minus. Again, you see this value, this is plus, right? So that means again that minus is changed to plus. So how many sign changes? 2 sign changes, right? So how can we conclude this? Number of sign changes in the first column is equal to 2. So that we can conclude 2 roots lies in RSP. So what about the third one? We have 3 roots, right? How we will judge whether it is in LHP or it can be in J omega also, right? How can we judge it? By seeing this number of change, we understood that 2 are in the RSP. Now we want to know whether the other pole, one more pole is there, right? Whether it is in origin or J omega axis or it is in LHP. How will you judge it? It is in LHP, right? How? If the pole.
Hello? Am I audible?
Yes, sir.
Okay. So how will you locate this? You just see the constants. These constants. Is there any constant, zero constant time in this? Because here it is 1, 2, here is 1, 3, right? All the S power is having the constants. If there is any zero constant exist in this, we can say that the poles are in, some poles are in J omega axis. We have only one pole and there is no zero constant time, right? So that means one root lies in LHP. Clear? Since the two roots are lies on the RSP, we can say that the given system is stable, unstable, or marginally stable. The given system.
Unstable, sir.
Unstable system because we don't have any pole on the imaginary axis. Clear? Now we will try different examples so that you will know the concept very well. You can work on this question. One more question you can now do. The question. The transfer function of the system is given as. The transfer function of the system is given as 5 multiplied by s plus 4, the whole divided by 2 s raised to 4 plus s cube plus 3s square plus 5s plus 10. Question is find the number of roots lies in LHP, RSP, and j omega axis. Can you find out and tell me? Using Routh array, you have to find. Okay. So from this transfer function, it is understood that the characteristic equation is 2 s raised to 4 plus s cube plus 3 s square plus 5s plus 10. This is our characteristic polynomial. And first of all, you have to construct the Routh array. So this s power 4, s power 3, s square, s raised to 1, s power 0. First, you have to place all the coefficients. Likewise, 2, 1, 3, 5, 10. Since this is not available, you can put it as 0. So what is the constant we are getting here? 1 into 3 minus 2 into 5. That means minus 7 by 1. It will come as minus 7. And what about this one? This will come as 10 by 5, 10, right? Yeah. Now this becomes minus 35 minus 10, that is minus 45. Minus 45 divided by minus 45 divided by minus 7. That means 45 by 7. This becomes 0. And what about the last element? It becomes 10. Clear? So how many sign changes you have observed in this problem? So this is which one? Sorry. Last one. Which one? I am not understanding. This constant you are telling. This one, 40, instead of 45 by 7, 35 will come. Correct only, na? Because you have to multiply this with this, right? So minus 35, again minus 10. So that means minus 45 divided by minus 7. So it becomes plus 45 by 7, right? So this is positive, this is positive, but you can observe a sign change here. This is minus, again this is plus, this is also plus. So how many changes are sign changes are there? How many sign changes are there?
2 sign changes.
2 sign changes, right? So one is minus plus 2 minus, again minus 2 plus, right? So you can conclude this number of sign changes is equal to 2. That means how many poles in LHP? Sorry, how many poles in RHP? Number of roots in RHP equal to 2, right? And now you tell me how many roots lies on LHP and how many roots lies on j omega axis. Can you tell me? So since there is no zero constant, right? So that means there is no roots lies on the j omega axis. We are having only 4 roots. Out of that, two is located in RHP. So obviously the remaining 2 will be in LHP. Since 2 roots lies on the RHP, we can say that the given system is unstable. Clear? Now we'll do one more problem. given the open loop transfer function g of s h of s is equal to 4 by a square, the question is test the stability of the system. So how will you find this? The question is, what is the characteristic equation for this? Whether it is s square no, why? So what is our characteristic equation? See, this is our transfer function, right? G of s divided by 1 plus g of s h of s. So this is our numerator n of s. This is our d of s, right? So the characteristic polynomial is 1 plus g of s h of s. This is the characteristic polynomial. This also you keep in mind. Don't make mistakes. So this is our characteristic equation. If the open loop transfer function is given, you have to find the characteristic equation using this relation. Sometimes it will give like this also. Okay, so this is the characteristic equation 1 plus g of s h of s. So in this case, it becomes 1 by 4 s square. So this is our CE. So what is the characteristic equation? S square plus 4 equal to 0. So this is our characteristic polynomial. So this can be written as s square plus 0 s power 1 plus 4. Clear? Now you can construct the Routh array. How will you construct? The highest order is s square. Next is x1 s power 0. First you locate the coefficients. It is 1. This becomes 0. This becomes 4. Since it is not there, you can put it as 0. Right? And anyway, this case we will come later. One more thing is you can directly check the stability here, right? This is a special case. Anyway, I will come to that case later, because here Routh array is becoming 0, right? You can see this value also 0, this value also 0. So this is a special case. We'll see how to deal this special case. Okay. Now, from this, can you find out the pole? From the characteristic polynomial? Yeah, S is equal to plus or minus 2j. We have two poles and both poles are located on the j omega axis. Right? So this is imaginary. This is real part. So if I locate these poles, 1 net plus j and 1 net minus j. What is the natural? Anyway, we already seen that if the poles are at imaginary axis, it will be a undamped system, or which kind of system? If the poles are purely imaginary, what is the nature of the system? Is it critically stable or undamped system or underdamped system? It won't be critically damped, right? Because obviously some sinusoidal time will be there. It won't be critical, right? Critical means there won't be any oscillation, right? This will be an underdamped system. Sorry, not underdamped, undamped. Because zeta, what is the zeta in this case? Zeta is 0, right? So it's an undamped system. So there must be a frequency of oscillation. What is the frequency of oscillation? It is equal to the magnitude of the pole, right? That we have studied, already studied. So it is 2 radians per second. So frequency can be find out by 2 by 2 pi, maybe 1 by hertz. Clear? Now we will see what to do when a 0 comes in the Routh array. That is a special case. Okay. So Routh's criterion, special case. What? First special case. The special case is what? In tabulation, first column elements becomes 0 and tabulation stops. What will do? Because when it's 0 comes means again the remaining element everything will be 0. So what is the solution if case arises? The remedy is replace that 0 by a time 0 and continue the tabulation. Then you can check the polarity. Clear? So this is the first case. It's a special case arises in the Routh array. If any of the element in the first column becomes 0, the tabulation will stop, right? So in order to continue that, what you have to do? Replace the 0 with an epsilon and continue your tabulation. Okay, now we'll see one case. So take this characteristic equation. The characteristic equation is given as s cube minus 3s plus 2 equal to 0. You have to find the number of roots in the LSP, RSP and the j omega axis. That is the question. How will you do it? How will you do it? S cube. There is no s square term right here. This time there is no s square, so 0 square is there. S power 1, s power 0. So this becomes 1. This becomes 0. This becomes minus 3. This becomes 2. So one of the element in the first column becomes 0. So what we have to do? Replace this 0 with this term. Right. Now we can continue the tabulation. What will be the magnitude of this one? It will be minus 3 zeta minus 2 divided by zeta. Right. This will be 0. What about the last element? This you multiply minus 0, this becomes 2. So now tell me how many poles are in the LSP and RSP. Can you tell? Hmm? Positive number, positive. We'll assume it as a positive. This is positive. This is positive. What about this time? Negative, right? Yeah, because we can write like this, right? This, if you take zeta common out, you can write -3 minus 2 by zeta. Right? If zeta is a positive real number, this becomes negative, right? So this is negative. Again, this is plus. So what about the sign change? There is a sign change from +2 minus, and again from this minus to this. So we have 1, 2, right? So number of sign changes is equal to 2. Clear? So how many poles in the RSP? And what about the number of j omega roots? Where it will lie? Huh? Because if poles should be, if poles are in j omega axis, 2 poles are required, right? Because it is always like plus j and minus j, right? Obviously 2 is required. Then now can you find the poles of this means roots of this polynomial, and tell me what are the roots of this polynomial using calculator? Tell me. -2, 1 and 1. It is coming -2. So 1 is in its left axis, right? Okay, I have some doubt in this. Okay, this we will confirm tomorrow. Okay. This problem I have some doubts. Okay, anyway, we will continue this tomorrow. Okay. Now we can stop our class, today's class. I have some doubts.